Okay, so I will start with the title. The title explains the whole talk, or it suggests that the talk is a salad of many things. So it's good maybe to not just look at the title. So high quality. Classical solution for the QCD relaxion. Very long title. So this is based on mostly on the paper that we just put last week. And this is with Abhishek Banerjee, my student, and George Levy. But also there's stuff here which is related to paper I wrote a couple of months back with Yoonjin Kim from Daisy, and also earlier work by again Banerjee. Yoonjin Kim, Alexei Macedonsky, and Mariana Safranova. So the model that I will explain in a second, what are the buzzwords is here. This is just a way to search for QCD, but with clock, with the change of energy level, which is surprising because the axion should not be searched with clocks. And this paper explains something which I think is interesting beyond the relaxion, related to phenomena which we call relaxion. So you'll see later, I will mention what it means. And all right, so this is where you can find, in terms of years, this is 20, the other two are from this year. Okay, so what are the buzzwords that appears here? First of all, there's high quality. As you know, axion models, they are susceptible to new physics effect, which do not respect the U1 symmetry, may be suppressed by Planck scale or by some ultraviolet scaling. So this is usually denoted as the quality problem. Classical solution means that the evolution of the relaxion will be classical, so we don't need to think about quantum spreading. And I should already say at this point that this should be contrasted with solution of the relaxion to the QCD CP problem associated starting with a paper by Nelson Prescott, where they show that you can solve the QCD, the strong CP problem, with relaxion, but you need to give up on the classical evolution, which give rise to all kinds of other issues. And actually, there was a paper by Geraldine Dorvan the same week that we were, I think like 1 week ago or 2 weeks ago, which called stochastic relaxion, which again analyzing the non-classical, the quantum regime of the evolution of the relaxion, trying to understand what's the role of this quantum evolution, and I think that they conclude that it works even in the quantum regime. But I think there are more conceptual issues to think about. I will not touch it. So I will assume very naive approach where I can think about the evolution of the relaxion as concrete. So I know exactly the deterministic, what is its time dependence. And yeah, the relaxion here is saying that I want to at least ameliorate the hierarchy problem. Okay, so I want to combine all of this. Great. So let me then begin. Maybe I will move this here. Are there more chocks or I dropped it?
In the Plastic glass over here.
Ah, great. So yeah, before I begin with the more detail, I just want to say something about the QCD CP problem. Because nowadays it's almost like a QCD action becomes like what supersymmetry used to be, and it shouldn't. So I wanted just to remind ourselves that I don't think that the QCD problem is a very severe problem. If we neglect the 7 loops contribution to the running of the strong CP phase, then in the absence of the 7 loop divergent contribution, okay, if we ignore this, which is if you put any reasonable cutoff, this is giving very small contribution to the standard model dipole moments, then this is becoming like a forever problem. Okay, there's hierarchy between the strong CP phase and the CKM phase, but they are not related to each other. And very much like we accept the flavor parameters being technically natural small, then the fact that theta bar is much smaller than the CKM phase. And this should not be. This shouldn't bother us. Okay. Yes.
Okay,
So
this is not really conventional.
this is why I want to say it. Conventional or not. I'm happy to discuss the physics. You disagree with this?
I completely disagree. But
Okay, that's great. So tell me why. No, I'm happy. This is why I want to make this. Why do you disagree? I mean, in the flavor puzzle, we have order 10 parameters. The hierarchies, which is as big as 10 to minus 10, probably smaller. And if I ignore the loop, then these are technically natural parameters, the no additive contribution. So what's the difference? I'm happy to hear your comments because I think that it's blundered by the community.
Sorry, but if you ignore loops, there is no naturalness problem anywhere.
So that's exactly my point. So if you want to see at which level the strong CP divergent is at 7 loop, okay, and it gives rise to log divergent, you can put any cutoff that you want to this log, put 10 to the 20 m plus, it's still going to give contribution which is very, very small, less than 10 or minus 10. So this is why I don't think it's a severe problem.
To me, even the hierarchy problem is not a problem of radiative stability.
No,
The
it's
problem
a
of scales. Yeah.
Yeah, it's susceptibility
You pick
scale.
a scale, so here you pick a number and you pick 10 to minus 10, and it could be 1.
No, I'm just saying.
Explain.
No. I'm just saying that the strong CP, in the absence of this, is protected by a symmetry which is CP.
Yeah.
Okay, you cannot say this for the Higgs hierarchy problem. There's no symmetry. That's the difference. It's very important. The difference. Okay, there is a symmetry. If I'm willing to neglect this, which has a super small coefficient, then this becomes a technical natural parameter.
Since you worry about quality, even there you should worry. Why did you impose this CP symmetry in the first place?
That is a different discussion, but we know that there are.
Related to
No, the CP is not a normal symmetry, at least for the standard model, so there's not a problem. Yes?
It's technically natural, but that's a different story from, technical naturalness has not really brought us many successes so far.
No, okay. I don't want to get into what success model. I'm just
You rely on technical naturalness.
yes. So under technical natural, if you ignore 7 loops, the strong CP is the technically natural parameter, so it doesn't subject to hierarchy problem, just a pattern the same as the flavor parameters. Exactly. You can see one by one. I'm very happy to have this discussion because I think that if you disagree with this, then you should go back to your QFTs. Yes.
Just to see if I get it right. So your
Yes.
statement is that
I'm going.
so the hierarchy between the CP values in the CKM and theta is order of magnitude similar to the hierarchy between the mass of the electron and that of the top, then you are not particularly.
No. So in the flavor puzzle, the hierarchy is much more subtle. Okay. In the flavor parameters, the hierarchy is characterized by the hierarchies of the masses times the alignment of the CKM element. So just the CKM element is subject to hierarchy of 10 to minus 5, that's the Gauss-Cope parameter. This is how much.
That's what I was saying.
Yeah. So if you include all together, you find that the hierarchies in the flavor parameters are in fact more severe than that. It's just that the flavor parameters are technically natural, so at any loop, this is protected. The strong CP phase, the only difference is that at 7 loop, you are going to get log divergent. Okay. So after these 7 loops, they are on the same footing. If you include this, then you'll see that indeed there is a very mild naturalness problem a la truth of the strong CP. Okay, I'm following truth here, technical naturalness.
No, that's a part I thought. So
Yes.
So you're just saying that it does not particularly worsen the flavor factor.
So the flavor puzzle is truly a puzzle. The strong CP is a problem, but in a very mild sense, in this sense. Okay?
Yeah, and that ignoring that sense, it becomes just a minor part of the flavor puzzle.
Yes, exactly.
Very good.
Yeah.
But
all right.
it's also fair to say that, we know, or there is a common law that there must be other sources of CP violation to account for baryogenesis, for instance, and then you must make sure that the problem does not arise in whatever extension you are thinking of.
Absolutely. So beyond the Stella model, there are CP problems. There's a well-known CP problem of supersymmetry. There's the CP problem of RS, and so on and so forth. I agree with that. Yes, they need to worry about that. But in the Stella model, you need to be careful when you talk about motivation. In addition, okay, so this is demotivate my current talk. Yes, I'm demotivating myself, but I think I'm honest. Okay? Nevertheless, it's interesting to think about the axion solution to the strong CP because it's maybe suggests other solution to other problems. And one example is of course dark matter. And if you can actually merge this with the idea of relaxion, then you can now correlate, if you wish, the solution to the strong CP problem with the solution to the hierarchy problem. Okay, so this is why maybe it's interesting. So the same solution, the axion solution to the strong CP might lend itself to other type of problems. So, for example, dark matter, and also the hierarchy in the case of the relaxion. All right, good. So now, yes. By the way, another way, if you like spurions, another way, I will just finish with that. Another way to see why you can separate these two is that this is proportional to the commutator between y up dagger, the argument of the determinant, and this is actually the product. This is why you can think of a solution like Nelson bar that's switching off this and switching this only at one head because it's a different spurion in terms of the dependence on the Yukawas. This is related exactly to this point. But this is a completely different topic that we can totally different discussion. All right, so now I want just to remind ourselves very briefly about the form of the potential for the axion solution to the strong CP because we need it. So as we know by Wapper-Witten, if we introduce coupling through the anomaly of the axion of the form, let's say over A over F, and I don't put here the all the coefficient here, G squared over 32 pi squared. But if we introduce into the Lagrangian this kind of coupling for the anomaly, then Wapper-Witten are telling us that at the minimum of the potential, A over F will be exactly equal to minus theta bar. And if it's dark matter or not, the RMS of the value of A over F will be exactly equal to minus theta bar. So if it's not dark matter, if it's a static solution, then this will exactly render at the minimum A over F equal minus theta bar, so solving the problem. And in the same way, if it's dark matter, it's oscillating exactly at that point, around this point. So again, the RMS will be zero. Okay, this is the solution. What will be important to us in a second is just to write the form of the potential. So you put this, you calculate the potential for the axion, and you find that it's given by very roughly something like m squared pi squared f pi squared times square root, and the form of this potential will be important for us. So let me write it: 1 plus z squared plus 2z cosine. We just write it as capital C of A over F plus theta bar, where Z is just the ratio between M up and M down, which is very roughly given by, let's say, 0.45. Okay, that's the leading order, the form of the potential. And usually in the literature, people are just showing the leading expansion in terms of the parameter Z, so then it just goes proportional to minus Z times, let's call the parameter here lambda QCD to the fourth, times cosine A over F plus theta bar. And indeed, as promised, the minimum of this is indeed when A over F is equal to minus theta bar. So that is solving the problem. Okay? So this is what I wanted to say. Because we are going to use this form, I wanted still to remind ourselves this potential. But this is what I'm going to say about the QCD axiom. The quality problem can be again seen if I look at the Petchy-Quinn field. So let's say that I'm writing a field phi, which is I can write it as a complex field, which is rho plus F square root of 2 e to the I A over F. Okay, and you can see the quality problem if you think that the UV physics that would not respect the U1 Petchy-Quinn, and then it will allow higher dimension operators that can write it like that. For example, phi over n divided by n Planck to the power of n times pi dagger of phi squared, for instance. And this would give rise plus Hermitian conjugate. This will give rise to a potential which is not aligned with this potential, to be of the form of F over n in this convention over n Planck to the n times f to the 4 cosine, and in this case it's n A over F. And you see that there's big misalignment in phase between these two contributions. So this will drive the axion minimum away from the minimum which is predicted by the axiom, and therefore it will spoil the theory. And the quality problem is saying that you need n in this convention bigger than roughly 7. So you need operator of dimension 11 or more in order to address this problem. And one solution that is there, so let me just write, quality requires that these operators so these operators do not spoil the success of the model if n is roughly bigger than 7. Okay, and one solution to this problem is to use discrete symmetry, Zn symmetry, which is respected by, maybe I should use the capital N, respected by gravity, and then the leading operator is going to be suppressed by the same power n here. So the leading operator that you can write will be of the 4 phi to the power of n. And if n is big enough, sorry, capital N, and if n is big enough, then you will not be worried about this operator. Okay, so this is one solution of the quality problem, and we are in fact going to use this in our addressing the QCD relaxion problem, and we are going to follow a paper by Hook, I think, proposing such a symmetry from 18. I will tell you a little bit more about this model, also Belen, Deluzio, Ringwald, and one more, I forgot. Study this. Okay, thank you. Because this model is leading to miraculous things. Okay, it's really a magical model. So it's I will say a few words about this. Okay, so now what I want to do is, remembering this, I want to go back to the QCD axiom, okay, which is the original model basically proposed by Graham, Kaplan, and Rajendran. And what I want to talk about now is the challenges of this model. because you see, I'm proposing that we are going to solve the challenges. So I want first to explain what are the challenges. So challenges of original QCD relaxion. Okay, so again, just to set the state, let me just write the Lagrangian of the relaxion. So the Lagrangian of the relaxion contains 3 terms. So I will write just the relevant one. First of all, there is a negative mass for the Higgs, which depends on the relaxion field. So I will write it as minus lambda squared minus G lambda phi times H dagger H. Now, because I'm using relaxion, from now on, I will not use A, so we are not confused. I will use phi for the relaxion. I hope that we remember to be consistent. But this phi eventually is an axion-like particle, so it's protected by a shift symmetry. There are many ways to UV complete it. I'm not going to show it in particular, but remember the phi is the same, is in the same footing as the A that I introduced before. So this is basically it's just the Higgs dependent phi mass. Okay, so it has 2 phases when phi is relatively small. Sorry, I should put here. No, it's good. When phi is relatively small, then the mass is positive, and we are in the symmetric phase of the electroweak. And you'll see that phi will evolve cosmologically. This will result in switching the sign of this mass term to a negative mass, and then this will trigger electroweak symmetry breaking. That's the first term. There's another term which is coming from the QCD axion potential. So as you know, even if you ignore this term, then there is a linear dependency on the quark masses. So there is a term which is called back reaction, which will depend on the Higgs wave. So the QCD axion to the leading order, I will now not use the full form here. I can just write it as something like Y up H. Okay, this is just M up, the leading contribution to the axion potential. In this case, the relaxion times the wave of the Higgs, and then times, I'm not careful here, lambda QCD or F pi Q times cosine pi over F. And again, let me ignore theta bar. We should remember that there's always theta bar here because this is coming from the anomaly. But I don't want to clutter the notation. So this is the Higgs mass. This is called the back reaction. And it is called back reaction because as long as the Higgs wave is 0, the up quark is 0, and then there's no potential for the axion or the relaxion in this case. So you need the Higgs wave to trigger the appearance of this term. This is why it's called back reaction. And finally, there's the last term, which is called the rolling, which is just given by G lambda cube phi. So this is called rolling potential. So this is the whole relaxion. Now, I'm not going to show it. I assume that you know it. If not, I won't have time. But the story of the relaxion is that it starts subject to this potential, which is that linear potential. So it's just rolling down. At the beginning, you put it in some random point. The Higgs mass is positive, so it's just rolling, and the back reaction is 0. Once it's passed through the critical point where this is 0, then beyond that, the Higgs wave is triggered on. And now you have a back reaction which is proportional to the amplitude is proportional to the Higgs wave times this cosine phi over F. And we assume that this is in the framework of inflation. So the relaxion is slow rolling. And the first point where the derivative will be 0 is where the relaxion is just going to stop. And this happens when the derivative of this term is equal to that. So that I will allow myself to write because this is important. And this is mostly what we need to understand the following. So the stopping condition is satisfied when basically G lambda Q times F is equal to Y up times V times lambda QCD cube times sinus pi over F.
The
Now-
classical, right?
What's that?
The classical.
Classical, and I insist that everything will be classical, correct? Otherwise, it's different. And what is nice is that if you think about the UV completion of this theory, you see that every single of the parameters is technically natural, and you can think about V as the solution of all of these parameters, assuming that phi is order 1. What you basically find is that V is G lambda Q F over M up, over Y up lambda QCD cube. Okay, and because everything here is technically natural, it seems that the scenario has a way to set V through technically natural parameters, assuming that you arrange for the stopping condition to be at the first minimum, okay, or one of the first few minimum. So that's how you address the hierarchy problem. And if it happens to be that this V is much smaller than lambda squared, then you make a progress in solving the hierarchy. It need not be all the way to M Planck. It's not going to be. In the theory that I will describe to you today, it will be up to 10 to the 7 GV. So this scenario, what it allows you in the original GKR, you can do a little bit better. It allows you to understand through cosmological evolution.
You remind me, Gilad, how far?
Why, just a second, just
Sure.
why V squared over lambda squared is of the order of, if we take the maximum thing is 10 to the 8, so this is 10 to the 2 divided by 10 to 10 to the minus 12. So you can naturally tell us why there's hierarchy between the weak scale and the cutoff of the theory of 12 order of magnitudes, not more than that. Sorry, Jay.
So what is, given some natural starting point for phi, what is the size of the field excursion that you need in units of F?
So yeah, that's the next thing that I wanted to show.
Okay.
Yes, so in order to do this, however, you see that it looks like here I'm describing non-compact field, and that's impossible because the action is, after all, angular variable. So I can think about, if you wish, UV realization of that, and then this term will be coming from the expansion of a cosine term. So in addition to this, so this is the usual axion potential. We understand this term very well. This F corresponds to the spontaneous breaking of the Peccei-Quinn symmetry. Okay. Here it seems that I need another parameters. So when you match it to a theory, you can see that this is part of a term which you can write as M squared H dagger H, and it's easy to write a theory like that, times cosine phi over another periodicity, which I will call capital F. And the interesting or the non-trivial thing about the relaxion is that this hierarchy that I just referred to has the following property, non-trivial property, that V over lambda is actually equal to or similar to small f over capital F to the power of 1/4. Okay, if you go through the whole exercise. And this is very bad scaling, because if I want 1 decade hierarchy between V and lambda, and after all, I want here at least 6 decades here. So 1 decade here corresponds to 4 decades between the periodicity of capital F, this additional term that breaks the shift symmetry that I just wrote here, and small f, okay? If I want here 6 decades, that means that I have 24 order of magnitude between small f and capital F. Okay, so that's really, really bad, okay? So it's telling us that for this hierarchy, f needs to be 10 to the 24 times small f. So this is much, much bigger than the Planck scale. And that, of course, is problematic. The way to address this is something which is called clockwork. It's relying on the U1 clockwork. And I won't have time to describe this, but this U1, again, is a global symmetry. So to solve this, you get basically big hierarchies, exponential hierarchies between F and F. So to make F much, much bigger than F, you need something which is called clockwork. It's very easy, but I think I will not invest the time in this today, which requires a very precise global symmetry U1 clockwork. And this leads to quality problem. Okay, very similar to the QCD axiom, in fact. So that's already one challenge that we learned about the QCD relaxion. But I want to claim that there's even another challenge which is more severe. So we found one problem. The other problem is a CP problem. This is also very easy to understand with what I wrote here. Buffer-Witten is ensuring that the minimum of this potential is at the CP conserving point. Okay, phi is equal to minus theta bar. Remember, I didn't want to add here the theta bar to drag it with me, but in this notation, it's phi over f equal to 0. That's in order to solve the strong CP problem. But here I'm actually balancing, and you see it over there, between two terms which have nothing to do with each other. They are not aligned in phase. They need to be independent, and in the clockwork you actually see this. So that means that the stopping point of the relaxion would be the generic point, naively. Okay? So if you wish the stopping point, let's define this as phi stopping, which is coming from the solution of that relation. Here, the minimum is generic. We have no control on this. And that means that in a QCD relaxant model, we have a prediction, but the prediction is that the strong CP is order 1. So we didn't solve the strong CP problem.
So
And in fact,
can I ask you something? So
yes.
Going back to the previous discussion, so I can sort of understand your point if you say maybe the full theory is the CP invariant and it is quantumly broken. Okay?
Yes.
Is your point of view?
Yeah, yes. If gravity,
Now, if you take the same point of view over here,
yes.
that the real theory is CP invariant and is somehow totally broken, then you would also solve the strong CP here.
Why?
Well,
This will
the
actually lead
minimum will be
to
at the CP.
no, it will lead to spontaneous breaking of CP. In fact, we have a paper on that. So the theory here is, if you take this approach, the theory here spontaneously breaks CP. And you can see, in fact, that it leads to mixing between the axion and the Higgs, which leads to a host of interesting phenomena, indeed. Yes. By the way, we also embed this in Nelson bar, which require spontaneous breaking of CP. So we have a paper which is called Nelson bar relaxion. In fact, that's exactly give you the source that breaks the CP. Yes, absolutely. So now, okay. All right. So now what I want to the way I want to continue now is tell you that there's something. I told you that the stopping phi over f is order 1. Now I get to the relaxon. There's something which I think is a tool in QFT because there's even more to say about the stopping point. And so I don't know about the time, but I have a feeling that I'm very bad, no?
We go for length of 1.
Okay, so I have like maybe
If the audience wants to allow you to push it till 10 to 1 or 5 to 1.
10 to 1 is fine. I will cover everything. Yeah, this model is like paella. So I told Guillermo yesterday I was in an amazing concert, and it involved like a combination of Spanish music with flamenco, jazz, and fusion. Amazing band. I was lucky that they are in Madrid today. Yesterday they were in Madrid yesterday. It's called Patak. So this model reminds me this because it's a paella of many result in relaxant/QFT/axion. So yeah, so I need in the paella. I need two more things. I need the relaxant to explain. I need this Hooke's model, and then I can combine it. And if we have a few minutes, we'll talk about the phenomenology. All right. So now I want to talk about something which we call relaxed reduction. This is about the stopping condition and something about violation of naturalness in the relaxion sector. Maybe we leave this on. Okay, so I'll still do it here. What do I mean by the relaxed relaxion? I mean that it's stopping at a very, very peculiar point in the field theory, which leads to kind of a singular or peculiar implication, which I think one can use beyond this talk. So what do I mean by that? In order to solve this equation, okay, I think I can cut on the corner and you can even focus just on this relation. This relation is the condition for the stopping of the relaxation. But this V, so on the right-hand side, I have only parameters which are dictated from the UV, they are not dynamical. The only thing which is dynamical here, I'm a little bit cheating, but I think you can get the picture. The only thing which is changing here is V. So, right, so, wait, maybe I need to go one step before. Yeah, because here I already took sinus phi. So I want to start with this relation, okay? So if I look at this relation, what happened is that I have G lambda cube F is equal to the electroweak scale. So I can replace this by exactly that term. To leading order, so y up, but now I write this as a constant. V electroweak is a constant. So y up, V electroweak, lambda cube QCD. And I will divide it by this, but this is a dynamical thing because V depends on phi. Okay, so I will divide it by y up, V as a function of phi, times lambda QCD cube. And this is equal to sinus phi. Sinus phi over F. Okay, this is pretty good description of what's going on. Now you notice, of course, this is trivial because everything here cancels. The only thing which is not cancelled is V electroweak over V phi, because V phi is a dynamical quantity in this theory of relaxation because mu squared, the Higgs mass squared, depends on phi. So if I will do this carefully, what I will find is that what I have here is a relation where I have V electroweak, which is what we measure, 246 GeV, divided by V of phi, equal to sinus phi over F. Now remember, we start from the left. We start from the point where at the beginning V was 0, and then it's becoming bigger and bigger when I'm rolling because of the fact that the VEV is increasing. Basically because of the fact that this, when phi is rolling, this mass is becoming negative, bigger and bigger and bigger. So at the beginning, this is very small, this is constant. So this ratio is much bigger than 1. So the condition for the potential, namely V prime equals 0, fails. I cannot solve it. That's not a surprise, because at the beginning, of course, the VEV is very small. Now I'm evolving the theory, so V increases from basically 0, it increases and increases, till I will be able to get values which is smaller or equal than 1 here, and then that will be the stopping condition of phi. Okay? That's how it really solves. You do this numerically, you really see how this is the way that you find the solution of this problem. But now here comes the important point. Phi, every time, this is periodic function, so when phi rolls, this is of course all the time changing between -1 and 1, okay? Every cycle when phi goes to phi plus 2 pi f, it goes back to itself. This is changing, of course, because phi is changing, but this is changing very slowly, okay? We can actually track how it changed, for example, over one cycle. So how much V changed when I take V of phi to V of phi plus 2 pi f. I want to see the denominator, how much it changed when I go to one cycle here. And that is very easy. This is how much this term is becoming more negative. This is how much the VEV increases. And for that, I can see actually that this is changed by basically G lambda F, or 2 pi F, every cycle. And this is very small, remember, because G is super tiny here. So I see from here that basically delta V over V, I can extract it, or maybe V delta V over V squared, because here it's V squared, it's just equal to G lambda F divided by V squared. This is the relative change in the value of the wave when I do one cycle of 2 pi f. And now I can multiply upstairs and downstairs by lambda squared. So I get that delta V squared over V squared is just equal to, this is exactly the condition for the electroweak. So this is basically Y up V electroweak lambda QCD Q divided by V electroweak squared times lambda squared. You want the question?
No, it's not.
So that is a crucial point. So that's V, each cycle of the back reaction, V is almost not changing. By how much it's changing relative to V squared? By this ratio. Now you can look at this ratio and you conclude that this is tiny, okay? Because here I have something which is of the order of smaller than lambda QCD, smaller than lambda QCD to the fourth, in fact, and up time like QCD squared. And here I have V electroweak times the cutoff, which we said is 10 to the 7 GeV or even more squared. So this ratio is super tiny, okay? We call it in the relaxion paper delta, delta square, sorry, which is much, much smaller than 1. It's super tiny, actually. It's 10 to the minus 10, or it depends on which parameter. Extremely small. And here's the crucial point. So when I'm trying to solve this relation, because V changes very small per cycle, then the first place I will find a solution is when this is almost 1. So that means that when phi over f is pi over 2. Okay, so the stopping condition is up to this small resolution parameter, we call it resolution parameter, is exactly, if delta goes to 0, that would be identical to pi over 2, but you miss a little bit pi over 2 by a factor of delta. Okay, so what we learn from here, maybe I will write it over there because it's very important, that phi stopping is not order 1. Phi stopping over f is almost identical pi over 2 plus the resolution parameter plus others even smaller quantities, which is quite remarkable. So this is a theory that gives us parametrically, not by accident, that the phase is exactly pi over 2. Okay, and for a while I was trying to do things like that. Okay, what can you do with the thing which exactly drive you to pi over 2? And just because of Hooke's model, in the paper of Bell and Ringgold et al., we finally found what to do with it. But right now it's a peculiar, if you wish, result. We, of course, corresponded this to the GKR, and they say, we kind of thought that this is the case, but we didn't continue. But the thing that they also have noticed is something which is related to QFT, which is very interesting, because this is almost exactly at the point where the derivative is maximum. It means that the relaxant is stopping at a very shallow point in the back reaction. So in the original paper and also in other paper, you see that people are drawing like Wiggins like that. That's not what happened near the first minimum of the relaxant. Because you're almost at pi over 2. At pi over 2, the potential, it's a saddle point. It's not a minimum. So the potential at the stopping is almost flat. Okay, this is where the potential stops. It means that the mass is very, very small. It's much smaller than the naive axion mass. So the mass squared of the relaxion is in fact not equal to lambda back reaction to the 4. So this is the QCD, the usual thing, m squared f pi over f squared. But it's this time this resolution parameter delta. So the mass is very, very small. So that's okay. That's a peculiar thing. And then, fantastic. Very helpful. And then there's one additional ingredient that makes it really, really cool. The additional ingredient is that the minimum of the derivative of the potential is sinus phi over f. So the potential goes like cosine phi over s. And if you look at this at pi over 2, it's 0. But if you look at the derivative of the potential, it's called like sinus phi over f, and at pi over 2, it's maximum. Okay, this is what we arrived at. So now remember I told you that there's mixing with the Higgs because there's CP violation. Think about the form of the potential as VH phi, okay? Conventional HA phi. What we just arrived is to a point that this is given by Y up H times lambda QCD U times cosine phi over F. But now I want to expand it around the minimum. So phi minus phi stop. And now if I look at the first derivative with respect to Higgs and phi, I find that it's proportional to sinus. So it means that I have big mixing with the Higgs. The mixing with the Higgs is not suppressed because it's proportional to sinus. Sinus pi over 2 is maximum. On the other hand, the mass, which is the second derivative, is almost zero. This is what I already established. So this is a situation that if you look for the relaxion as if it's a Higgs portal, because it mixes with the Higgs, you'll find that relative to its mass, the mixing is huge. So it looks like a Higgs portal, which is very, very unnatural by factor of delta. Okay, and in this relaxion, we analyze the phenomenology of that. We show that you can get, let's say, if it's at a region of beam dump, if its mass is, let's say, between 100 keV and 1 GeV, the beam dump can look for this as if it's a Higgs portal, but the coupling will be way, way above what you think about the naturalness bound. So this will look like a very weird creature. This is why we call it relaxion, because the relaxion is not only solve the hierarchy problem for the Higgs, it's also its own parameters are very, very weird. And this is, of course, continues also if you think about the relaxion in the more natural place where it's very light, if F is big. So if the relaxion is very light, it means that it will have coupling which are characterized by 1 over F, but times sinus theta, but its mass is much more suppressed. Okay, so it's a weird QCD axion. Okay, it doesn't obey the usual, DFVZ or whatever QCD axion model you like. The parameters here will be very, very different, very weird.
So the things that you said, are they true of the original relaxion model?
Yes.
Okay.
Yeah. So that was fun. So when we figure out all of this, we send them and they say, oh look, we have even a line. I imagine that we think that it doesn't stop at a generic point, it's a flat, but we didn't know what to do with this fact. So we wrote a whole paper about this line, if you wish. Yeah. So yeah, that's generic as long as you have classical evolution and you're stopping near the first minimum. Now I should say that in principle, with carefully tuning the initial condition, you can stop at a much further minimum, but this is not generic. Generically, you will stop at the first few minimum, otherwise you're not controlling the theorem.
And sorry, this assumption that you are classical evolution, shouldn't you have to worry about quantum fluctuations if you are so flat there that could take you out?
Yes, you should, but there's a condition and you satisfy. You take this, now you go backwards and you, of course, you need to make sure that the phi dot over h squared is less than v prime, if I remember. Okay, so you take how much you evolve per inverse Hubble time, and you need to see that it's less than v prime, and then you know that you are controlled by the classical evolution. But it's make harder, so you're right. There is
you can satisfy that and the third answer.
Yes.
Okay,
in fact, for the theory that I'm going to show, that the strongest bound is not coming from that, but from tunneling. But yes, you should worry about that.
No, it's just a comment about what you just said. I think it's not. I mean, it's not true that it's non-generic to stop it like further minima. It just depends on your initial slope in comparison to Hubble. Like if you have enough Hubble friction to stop at the first minimum, then you stop. Otherwise,
I would agree. Yes.
Initial slope so that the velocity is larger. Then in the end you stop.
Right. I should have been a little bit more precise because indeed, phi dot is exactly equal to v prime over h, so you can see relative to that. Thank you.
This is very generic in the original paper.
Right. Okay. Great. So now we understood the relaxion. And
like 10 minutes.
Yes. But it's good because I'm at the last. Thank you. So now the last thing is to try to combine this in our PAIA with Hooke's model. Okay. So, and again, regardless of all that I said, so this is another part where it's a modular, like the relaxion. You can use the idea of relaxion independent of solving the hierarchy problem. I think that this is a tool. So same thing, you should be aware if you're not on Hooke's model. So this is a model which is based on ZN axiom QCD. And the idea there is that you have n copies, or I think I should try to write here capital N. Never You have n copies of the standard model. And the symmetry is that the Lagrangian of a copy of the standard model, let's call it K, under this ZK goes to LSM K plus 1. So we have n copies, but somehow through reheating, we only occupy the standard model, sector. But if I look at the potential at zero temperature of the axion, it has the following property. I won't write the full Pechi-Quinn model. I think it was in the paper by Belen, but you can see that the full potential for in this case it's the relaxion, there it was the axion, is given by sum of the individual potential, which let's call it m pi squared, f pi squared, but with an index I times cosine phi over f minus, now I switch on theta bar because it will be important in a second, plus 2 pi I k over n. So the only difference from just n copies of the standard model in the axion sector is that the coupling of the axion, because of the way you realize the ZN symmetry with the Pechi-Quinn symmetry, that you have one axion, but it couples to a K sector and a K plus 1 with a phase 2 pi I K over N. Then it's very easy to realize that. So this is the axion potential, or for us, this is the relaxion potential. I will break this ZN, but in the Hooke's model, it is not broken. The ZN is exact. Now, actually, maybe no, maybe I should not have written it like that. Sorry, I should first have started. Yeah, sorry. So I should first have started with the full potential. So it's important, in fact. Sorry about that. So 1 plus z squared plus 2z cosine, and now the argument with the phi over f plus 2 pi k over n. Okay. So this is after all the original axion potential, and it's the same. I need to sum over all sectors. So here there's a sum. Here I'm getting messy. This is why I wanted you to have the slide. So in the slides, everything is organized. There are all the references, by the way. But this is the form of the potential. Now, what Hooke noted is that there's something really magical about this. Let's first of all expand it to leading order in Z. So I get that the potential, the full potential, is proportional to the sum of cosine phi over f. Again, because of time, I don't write 2 theta bar, but phi over f plus 2 pi k over n, sum over k between 1 and n. Okay, the coefficient is the same, so we don't care. Now, this is of course just summing unit vectors on the unit circle, right? So this sum is obviously 0. Okay, it's very easy to see that this sum is 0 for any k which is bigger than 1. So that means that if I look now at this formula, and like we always do, I expand it in higher multiples as different function of a different power of z, then the first power where this will not be 0 is just the nth power, because if I write cosine to the power of n, then I can expand it as cosine n, cosine to the power of n theta. I can expand it as a sum which contains cosine n theta, and cosine n theta is invariant under this symmetry. So that implies that the first term, which is non-zero, non-vanishing in this sum, is proportional to z to the n cosine of n times a over f, basically. But what is important is that, and this should be capital N. What is important is that I found something really weird. I mean, Hook found, Hanson found, that the QCD action potential is now suppressed by this parameter, which is 0.4 something to the power of n. So if I have n big enough, depends on your taste, let's say n equal 10, it means that the potential of the QCD action will be shallow by factor of 3 order of magnitudes. So that's a way to, if you wish, get net, and it's natural. That's a way to get away from the QCD line, not to the right, but above, which is very good for the experiments, okay? All the experiments are obsessed, of course, with trying to search for the action parameters, and there's always 1 over f here as a function of n. The QCD axiom satisfied n times f equal lambda QCD to the 4th, roughly, so it's here. So this is lambda QCD to the 4th. But in axiom, in the Zn axiom model a la Hook, you can actually go here because you have a suppression of factor of z to the n.
What is Z? Yeah.
Z is m up over md. Okay, the isospin brackets, roughly 0.45 or something. Yeah, I mentioned it maybe too quickly. Okay, so that is very nice feature. And now, okay, so I didn't have the time to tell you in detail what is the model, but what we are doing in our situation is now we combine the fact that we stop at pi over 2 with Hook's model, doing something very, very trivial. So if Zn is in fact Z4n, and for example, let me take the simplest model, Z4, then I have 4 copies of the standard model. Here I have a coupling which is, let's say, over A over F plus theta bar to GG dual. Here I'll have A over F plus theta bar plus pi over 2, GG dual, and so on and so forth.
So you are taking it precisely because you don't want the minimum at C, or you want it with 5 over 4.
Exactly, that is the trick. So I did the whole talk just to get to that point. So the point that I'm making, if we break the Zn symmetry softly or by small, very small UQAR, such that if you wish that this term is dominate the back reaction, it will stop at what they think is theta plus pi over 2, but the effective theta bar plus pi over 2 for the standard model, so here this will be, let's say, the standard model, will be at the stopping point where the effective theta bar is 0. And that's how the model works. Okay, very simple. Now, the genuine phenomenology is that we don't stop exactly at pi over 2, we stop at pi over 2 plus delta, remember the resolution parameter. And because of the tunneling and all of this delta is smaller than 10 to the minus 11. Sorry, bigger than 10 to the minus 11. So we have a prediction for where the minimum of the action potential, relaxation potential is. And this is roughly 10 to the minus 10 up to 10 to the minus 11 away from 0. And that, of course, means that the dipole moments experiments are just behind the corner to search for that. And then there are many, many experiments which are looking for axial times scalar coupling that can search for that. In addition, you can look for this with clocks. I won't have time to discuss this. But now, because we control the deviation from 10 to the minus, from theta bar, we now get host of experimental relation that experimental observable that can search for such a model. So this is super nice, and also the mass is slightly smaller. And finally, because it's based on Zn, you can solve the quality problem both of the axion, but also of the clockwork. And I think I will stop here. Sorry for taking too much time.
I think there were plenty of questions. Thanks, Gilad. Perhaps we can allow for one quick one. If you're up for it.
Sure, yeah.
If there is any. No, people want to go for lunch. Okay.
Yeah, it was
Then thank Gilad again.